My name is Carl Jai. These are my team members, Mohammed Arif and Christian Bernard. Our faculty advisor is Dr. Bilal El-Zahab, and our project is the three-dimensional solar panel. Now, a quick introduction into solar cell technology. Solar cell research and development has been around for many years, but in recent times they have become more popular as a means of primary energy generation. Solar cells are also known as photovoltaic cells, and the main idea behind it is to convert sunlight into usable electricity by a photoelectric effect. Now, solar cells, such as the one we can see here at the bottom left, can be electrically wired together to form a module. And a module can then be wired together to form an array, and this will produce the maximum energy generation. Now, modern solar cells, as we know them today, were first manufactured and produced back in the 1950s by a company called Bell Laboratories. And the first application of these cells was seen in 1958 at a launch of a satellite called the Vanguard 1. Now, for our panel statement, we want to basically address pollution by reducing the overall carbon footprint. But I'm doing this by implementing our three-dimensional design to then increase energy generation. And once this is done, we can hopefully see more solar power plants rather than fossil fuel polluting that we can see here in the picture. Our motivation for our project was fairly simple. Reducing the dependence on fossil fuels was at the top of our list. As we know, the demand for energy is increasing on a daily basis, and fossil fuels such as coal, oil, and maybe even natural gas will become scarce. It is for this reason that we plan on harvesting as much energy from the sun as possible, for the sun is basically an unlimited energy source. Now, we want to design our solar panels in such a way that it's portable enough to reach remote areas that are basically off the electrical grid.
Our objectives are to maximize the sunlight absorption by utilizing the 3D geometry. To do that, we potentially apply our 3D geometric shape in the residential area to further, if we look into our design goals, or global aspect of our design. As we know, the world's demand for power increased, so does the demand for fossil fuel to generate the energy also increase. To overcome our future generation energy problem, countries around the world are shifting towards renewable energy, in particular solar energy. If you look at the European countries like Germany, Germany produces about 3% of its total energy from solar energy. It plans to increase that generation by 50% by 2050. If you compare the United States only produces 1% of its total energy from solar energy. As you can see, in 2010, it was the largest solar producer in the world. Our design goal is to find the most efficient geometry, which is cost efficient and easy to manufacture, and also it upholds the environmental regulations. The material that we are using is polycrystalline, which is easily available, is cost effective, and relatively fairly efficient.
Now, for our initial design, we have proposed a pyramid-shaped solar panel. Upon further investigation and consulting with our advisor, amongst others, we decided not to pursue this design, mainly because the pyramid-shaped solar panel would rely too much on alternative methods to increase energy generation, such as reflectors. Since the pyramid-shaped solar panel, a lot of faces of it would be shaded and not in direct contact with sunlight, we would have to then introduce reflectors to the design to increase the energy generation. And with the main goal of our project in mind, to just increase energy generation rather than to rely on alternative methods to do this job for us, we decided to discard this design altogether and basically use reflectors as an optimization.
So for our final design, we chose to use the parabolic curve geometry. We use this to maximize power generation because it remains at or around 90 degrees to incident sunlight at all times, which is the angle for maximum absorption. Also, since each solar cell is angled at a different orientation, it can effectively capture off-peak sunlight such as morning and afternoon hours, whereas the flat panel works most efficiently only at midday when the sun is directly overhead.
We did a stress analysis of our design, and by using the 50 miles per hour wind speed, we proved the strength and the safety of the design. And it shows, the simulation shows it can withstand the maximum pressure of 7.2 kilopascal, which is pretty safe, which can withstand hurricane conditions.
So for how it works, these cells are made from silicone, which is a very good semiconducting material, which means it can transport electric current very efficiently. The cells are made of two layers, which is a positive and a negative layer. When the photons are absorbed from the sunlight, it releases electrons. The electric circuit then captures this flow of electrons, which is known as the photoelectric effect. This is an equivalent circuit of one of our solar cells. As the diagram shows, the diode represents the PN junction, which is the junction between the positive and negative layers. There are also two resistances in this circuit. The first is a shunt resistor, which is due to manufacturer defects, as each solar cell can't be manufactured perfectly. The second is a series resistor, which is due to contacts with the solar cell, mainly due to metal contact on the top and rear.
Now for the positioning of our panels, basically every type of solar module wants to be directed towards the equator. So for countries all located in the northern hemisphere, we want to basically point our panels due south. And for countries all located in the southern hemisphere, we want to then point solar panels all due north. So since our testing location was here in Miami, Florida, and we are located in the northern hemisphere, we're pointing our panel south. And once we have established that, we want to put it at a specific angle towards the sun to maximize our energy output. And this angle has been known as a tilt angle. And the tilt angle can be calculated for various seasons throughout the year, as seen here by these equations. If we take a look at the bottom left picture right here, we can see that for the northern hemisphere, the sun is the highest in the sky during the summer months and lowest in the sky during the winter months. So the angle for the winter months will be a lot greater than, say, for instance, those that are in the summer months. Now, for testing, what we have done is we built both our curved solar panel and a regular flat panel, and we put them side by side for comparisons. We then hooked up two multimeters to each panel to record the current and the voltage in 5-minute increments for a full solar day. So basically from sunrise till sun up. And these multimeters were equipped with a RS-232 capability. Now basically this allows us to then plug the multimeters to a computer, and it would then measure real-time data. This is a screenshot of basically what the program does. We input our time, which is from sunup to sundown, and we input our time interval, and it will log the data every 5 minutes. Now this here is radiation data that we use for the analysis of our solar panel, and it is obtained from the NREL. It's the average monthly solar radiation data for every month in Miami, Florida, and it is basically observed over the span of about 11 years.
So for our calculations, we did theoretical calculations to confirm the accuracy of our experimental results. These are based off of a generalized formula which depends on 4 factors, which are the surface area of the solar panel, the solar irradiation, efficiency, and performance ratio, which each will be explained in the following slides. First is efficiency, which also depends on 4 variables. These are the open circuit voltage, short circuit current, input power, and fill factor. The first step is to measure the voltage and current directly from the solar cell. Once these values are obtained, we could calculate the normalized open circuit voltage using the formula shown. From here, we calculate the fill factor, which is just the ratio of maximum power to the product of voltage and current. The last variable for efficiency is input power. For solar power, there's a general input of 1 kilowatt per meter squared. Based on our area of 0.015 meters squared, we obtain the input power for each cell, plug all of these variables back into the efficiency formula to get an approximate efficiency of 11%. For solar irradiation, as the diagram shows, this depends on 2 main angles. The first step is to calculate the declination angle, which depends on the day of the year with January 1st being day one. Using this declination angle and also the latitude of the location of testing, we find the elevation angle. This table shows the angles calculated for one of our days of testing. These values may not be perfectly accurate since sunrise and sunset hours may change and may not always be exactly 7 a.m. and 7 p.m., therefore changing the hour angle. This chart shows worldwide solar irradiation, with yellow being most irradiation, red being less. From here, we get our value of incident solar irradiation, which is then plugged into the formula, along with the elevation and tilt angles to obtain the solar irradiation for each hour of testing. This is the performance ratio table. This basically shows the factors affecting performance ratio and their values. We plug this in to find an overall performance ratio for each day of testing. And once we obtain all these four factors for energy generation, we plug it back into the generalized formula for energy to obtain our theoretical results for both days of testing for both panels. And here they are in the table shown in both English and SI units.
Okay, after doing the experiment, here's a graph of voltage versus time for two different panels, flat panel and curved panel. We did the testing of two different conditions, sunny day, which is an ideal condition, and overcast day, cloudy condition as well. As you can see, the voltage does not change for both panels. And following the current versus time graph, as you can see, we did the testing again for two different panels for two different days, sunny day and the cloudy day. The current does change for the curved panel, but it doubled. And following up the power versus time graph, we calculated the power by the part of current and voltage for two different panels as well for two different days. And then we, after doing the power versus time graph, we calculate the energy generation by integrating under the power curve.
Now, as Mohammed just explained, once we integrate it under the power versus time curve, we then obtain the energy generated for a specific day. And what we have here is the energy generation for a day of testing on overcast conditions and a day of testing under relatively good conditions, a sunny day. And we can see here the energy generation for both the flat and the curved panel. As we see here, the curve produced significantly more energy than the flat panel in both the overcast and the sunny days. Right here we have a graph of the percent improvement from basically a flat panel to a curved panel. And it's important to note here that the biggest improvements are at the very beginning and at the end. And what this represents is basically sunrise and then sunset.
So for our error analysis, we compared the theoretical and experimental results. As you can see, both errors were relatively small, but the error for the cloudy day was greater. This is because it's compared to ideal condition results, and obviously the sunny day will be more similar to ideal conditions, whereas the cloudy day will be less accurate.
To use the energy generated by our curved panel, we can use the energy by implementing these three components. A charge controller, which regulates the charge to charge the battery, and it does not overcharge the battery. After the power is stored in the battery, which is stored as a DC volt, as we know, the average household application uses AC power. To convert the power from DC to power, we use an inverter.
Now, as with any design, there's always room for improvement. And we came up with a few points that are basically recommendations into how to optimize our solar panel. Well, first of all, we use for our panel polycrystalline cells, which have a relatively good efficiency of approximately 14%. We can easily substitute these out for a better solar cell, which is made of a monocrystalline silicon. These usually have a much higher efficiency than polycrystalline, but are also much more expensive. Now we calculated some numbers just to show you the percent increase from moving from polycrystalline to monocrystalline. And the increase was about 26%, which is very significant. We have to note, though, that by implementing monocrystalline, the overall price of the module will also increase. Now, another recommendation is keeping the cells cool, because as temperature increases of the cell, the efficiency decreases. So by mounting some type of cooling rack, or maybe introducing some type of airflow to the module to decrease the temperature to help us increase the energy generated. And another important recommendation is to maybe implement an automatic tilt system. This would basically prevent homeowners from going outside their house to manually adjust the panel during various seasons throughout the year.
Based on the two different panels, the energy generated by the curved panel, as you can see, and the flat panel and the curved panel is rated maximum at 18 volts. To do the conversion and raise the scale to 100 watts of panel, which is available commercially. And furthermore, to do the cost analysis, we did the pricing available from FPNL, which is 10 cents per kilowatt. If you do the cost analysis, you can see the curved panel saves about 83% compared to the flat panel. Here's a cost analysis of overall our project. I think includes the solar cells base, which is made of plywood, multimeters, cables, wires, and lab and machining. The overall total cost of our project is $500. And here's a quick look up of our timeline, which spans from September to April. Some references of our design, our research. Any questions?
Are there any questions? Dr. Bezos smiling. I know he wants to go. Go ahead, Dr. Bezos.
So I have a couple of questions. Can you go back to the plots of the voltage that you showed? So it seems to me, based on, say, the curvature of one, maybe go a couple before. Yeah, so for instance, let's go to current. Right? So based on the curvature that you see, right, you'd think that the flat plate at, say, noon would have a peak that's higher than the curved plate no matter what. Why don't you guys see that?
From when we tested, we wondered the same thing, because during our testing, I think it's because our panel is exposed at all times. During midday, it's also fully exposed, whereas the flat is also fully exposed, but it could be a deficiency in the solar cells or in the wiring, but we expected the values to be a lot closer at midday between the curved and the flat panels.
Yeah, it just seems like there's an offset of any value, right? So it just seems to me like the offset is there in the circuit itself and not
Yes.
with the actual curvature. That makes a huge difference in the results that you're showing, right?
Yeah.
Okay, can you go to your theory as well? So that there was a plot where you showed kind of the angles. Yeah, there we go.
Yeah.
Okay, so this is a two-dimensional plot, right? But you have three-dimensional angles associated with your prediction, right? So you have both the vertical tilt angle and then the horizontal tilt, right? Did this incorporate that additional degree of freedom in the analysis?
Well, actually what we've done is that we've incorporated these calculations that you see right here and used other angles that we used to build this panel and incorporated them that way.
What does that mean?
Yeah, I mean, there's some more angles that are not shown in this specific picture. As you said, it's just a two-dimensional picture.
So where do those come into play in the formulas that you showed?
Well, it's not depicted in this particular formula. These formulas are shown just to show you the solar irradiation used to calculate.
Well, it just should.
As the
It seems
table
to me if
shows.
you're going to predict based on this curvature, right? You want to incorporate.
Yeah,
all
that's why we need to calculate the irradiation and efficiency ratio for each cell for the panel. So each cell is going to be different with different angles. As we did, like our table shows different angles for one of the cells we use. Just an example calculation, because we can't put every
Because
table.
the calculation,
I understand.
actually it's different every minute. Every minute it's very different. It's not the same thing.
So it just helps us to understand that you guys did that, right?
Yeah,
And if we don't
yeah.
see it,
No, we
it's
did.
very hard to see.
That's
So
why
how
we
did
have
you
a partial
actually pick
tape.
the shape that you have here? How did you pick this shape?
It was basically sitting down and brainstorming, also with our advisor and came up with the idea that let's introduce a curved, like parabolic shape, like kind of like satellite shape, if you will, like a cone shape, which it would be easier to manufacture, and it wouldn't be difficult to place outside of a house rather than a pyramid just sitting outside the house or on top of a roof.
So did you try any other angles?
Also,
You just
as
picked one angle?
as we mentioned in our initial design, we planned on constructing a couple different prototypes, such as the pyramid, the cube, and also another like inverse of this, opposite to this cube. But we didn't have the funds to construct each one. So doing the testing, we just did basically test to determine which one we think will be most convenient for
So
us.
you guys just couldn't take the panels off and put them on another piece of plywood?
Well, no, the thing is we have to stick the cells on the panel because during transportation, we can't have it moving around. Cause I don't know if you can see it, but a lot of the cells are actually broken right now due to transportation. They're very fragile.
Where do you transport that for?
Like taking them to the car, taking them out the car.
Alright, yeah, that's fine. Okay.
They're very fragile.
That's
Even
fine. Yeah,
when tabbing
yeah.
all the cells,
Sure,
they're
sure.
very fragile.
Okay.
That's it, Dr. Mason?
Yeah, that's fine. Yep.
All right, any other questions? Yeah, Dr. Tamonte and Dr. Monroe.
The questions I want to ask is, again, a little bit on the curvature. I would have assumed that you would have optimized the shape of that curvature based on the relative position of the sun to the ground. Was that in your thought process?
Yes, it was. But once we had built it, it was kind of difficult to remove it and then kind of rebend the wood to a certain
But
angle.
I actually probably would have been less,
A lot wider.
yeah, but it would have been theoretically determined. I'm a little surprised you didn't.
Yes.
Second question I have is, the flat panel and the curved panel, was the shunt resistance between those two systems exactly the same?
We did not calculate the shunt resistors because basically the shunt resistance is just for one cell. Basically what that was is just a circuit drawing of what a solar cell is.
Okay, so let me ask this question then. You know that the overall resistance of this panel and the flat panel that you presented to us were the same?
Theoretically, yes.
Theoretically or
Yes.
actually?
Once we measured, the resistance varies because you apply load to it, you apply multimeter, so the resistance it varies a little bit with the cables on there as well.
Like he mentioned before, how the graphs, the flat panel should have been closer to the curved panel at midday. We believe because of the cell manufacturing deficiencies, like we explained, some resistances in some of the cells are greater than others because each one is not perfectly manufactured. So that will give us a greater resistance, and obviously in the flat panel, this is why it did not compare to the curved panel at midday.
Okay, so let me ask you this question. How do you compare flat panel output to curved panel output and make statements about curvature being the improvement if all things other than it are held constant?
Testing. When we tested both panels side by side under the exact same conditions.
Can I throw a suggestion?
Yeah.
You could have taken all of the panel, all of these photovoltaic cells off of the flat panel, put them on the curved panel, right, and switch back and forth, and then say, hey, look, we put them on the curved panel, it still works perfectly, or it still has a higher voltage output. And we put it on the flat panel, and it still has a higher.
And that's exactly what we wanted to do, just to point out, exactly what we wanted to do. But the thing is, once the cells were stuck on the panel, we couldn't remove them. You would actually have to break all of them.
Well, no, I understand that, but you
And we were
glued
very
them down,
limited on the
right?
amount of
Yeah.
cells we had, because we actually did do that. We actually did break a lot of the cells off the flat panel at first. But because we were limited to cells, we couldn't do it on this one.
I have one last question. Could you put up the curve that shows sunset and sunrise?
Time and intensity.
Okay. Based on this, it's telling me that there is more output and improvement, it's more improvement, okay? That's not telling me that, okay, so I guess I understand.
It's basically, well, once the sun comes up at sunset, it hits these cells at a certain angle. And the flat panel is just It's just flat, so it doesn't reach it the way it does this, and also with sunset, both sunrise and sunset.
The outer cells are exposed to 90 degree at sunset and early mornings.
Understood.
That's where it makes a difference.
Okay, thank you.
Any, Dr.
My
Monroe?
questions are very similar to Jim's question, because intuitively, if you were to have the curvature opposite to what you have there,
Like a
what-
dome shape.
Yeah, like a dome shape, what would you expect?
We would expect more or less the same. It would probably be a little bit different because of, it depends
But would it
the
be better?
bowls, the shape of.
Well, let me rephrase my question. Would it be better than the flat panel or worse than the flat panel?
We would have to actually do some theoretical calculations on that, but it should perform better.
It would be better than the
Why?
flat panel.
Why?
Because it's exposed to the rays at 90 degrees most of the time compared to the flat panel. If the sun is here, it's not perpendicular. If it's curved or a dome shape, it's actually hitting at the 90 degrees.
And it's
So
important
it's
to
still
note
better.
that at sunrise, once the sun comes up at a very weird angle, it will still hit most of the cells that are at a 90-degree angle, rather than the flat panel just being flat and hitting it at a slightly less angle.
I'm not sure, but my other question has to do with cost. You were saying that with the monocrystalline solar cells, you should have better performance. How do you compare the better performance with the increased cost?
Well, basically, it's the pricing of the cell itself. Once, if you were to implement the monocrystalline cells into, let's say, regular solar panel, it would be a lot more expensive because they're a lot more expensive to manufacture.
I know, but relatively 20%, 10%.
Oh, the cost.
I think you said the performance is about
The
26%.
performance, the
The
energy,
performance.
no, the energy increase.
Is about
The energy output increase
26%.
is about 26%.
And so the increase in cost would be percentage-wise approximately what?
Well, percentage-wise, since we would say, based on the cost that we see from manufacturers, the monocrystalline cell compared to such a polycrystalline cell, it also depends on the amount of efficiency. Some are 17 for monocrystalline, some are 18. But the price range is almost double, not exactly. It all depends on which type you would want to buy and from which manufacturer. Certain manufacturers make them better than others.
So on the whole, you would say you would pay 50% more for a 25% increase?
More or less. It doesn't have to be, it depends how you buy it in bulk or not, but yeah.
That's it,
That's
Dr.
it.
Monroe? Any other questions? Yes.
What would you do differently if you were to do this again?
I would actually change the material. Since these panels are fragile and you cannot bend them or they're not flexible, I would change the material and choose a thin film, which is a flexible material, and have it placed all over the panel and use all that empty space that you can see. And that would be another suggestion.
Also, instead of buying, because the cells that we bought, they were all untitled cells. So it was just a raw cell, no wiring. Well, now we know that there's tab cells available that you can buy, because in the process of soldering all the wires to the cell, we broke a lot of cells, damaged a lot of cells due to the heat from the soldering iron. And also for testing location, we have to find basically a better location to test, maybe an open field. But our problem was we didn't have, in an open field, you don't really have power outputs to plug the laptops in, because we needed the laptops to charge in order for us to measure all the data.
But would you keep the same setup? I see that your proposed design, you had a cube and you had a pyramid, and now you have.
The ideal situation for us will be to construct all the prototypes and test each one side by side to see which one is the most efficient for us to put out there and market for everybody. But since we couldn't construct each one, but if we could, that'll be the ideal situation. Try each one and by testing determine which one will be best suited for us.
And or come up with a special algorithm that would solve for every shape known to man to determine what would be the best shape to use.
Any other questions? Yes.
One question. You
guys as a team decided that you were going to change off who's going to speak one at various intervals. How did you come to that?
Can you speak up a little louder, please?
Yes, how did you come to the decision that you guys were going to change off who speaks one?
Because we didn't want to everybody just go at once, you know. If we talk too long, it becomes repetitive and boring.
How did you allocate the time to each person? How did you make that decision? Who's going to speak one?
Well, we basically just, we looked at the overall presentation, looked at how many slides we basically had. And then from there, we went over the PowerPoint a couple of times. And from there, we made necessary changes like, okay, wait, I think it's better if you go at this time. You go right after I do this slide, present this slide. And that's how it went. So as the more we practiced, the more we changed who talks and what piece, who takes over.
Thank you.
All right, and I just have some closing comments. I'm excited to see that you went through and did the optimization process and you realize that it would have been more saleable to automate the tilt angle and also to test the various efficiencies. And the optimization pretty much told you what you needed to do, what direction you needed to move. That's, I was very impressed with that. So those are my closing comments. Thanks very much.